Okay, hello, good day everyone. Today we will have Franco Moitzi giving a talk to us about work on finding empty spheres, which are important for calculations in multiple scattering theory. Franco is currently a PhD student at the University of Leoben in Austria, and he has visited Oak Ridge and worked with us during the last year, working on multiple scattering methods for alloy system defects and alloys magnetism and relaxation of structures. So Franco, please go ahead.
So hello everyone. Thank you for the nice introduction. So today I'm presenting a pre-processing tool for making open structures ready for KKR calculations. So firstly, I will point out the main difficulties in calculating structures with low backing in Green's function-based KKR methods or multiple scattering methods. We'll use these terms, both of them. And then I will describe an algorithm that is used for filling such structures quite efficiently. And I will finish with some selected results where this pre-processing tool has already found some application. So the exact potential of a structure is mostly composed of some spherical symmetric part around the nuclei and some more repulsive and almost constant part in the interstitial region. And the connected electron density is mostly more complex, but is still following this same partition. However, like our KKR methods rely heavily on, or actually rely only on an atomic sample basis set. And this is quite difficult. This makes it actually quite difficult to calculate structures which have a lot of large interstitial regions. So mostly one needs to add their additional expansion points to describe the potential and density better in these regions. And this can be achieved by putting these so-called empty sites there. So these are basically sites which don't have any core charge, but we still treat them like normal, regular atomic sites. And a prominent example here is actually the silicon structures. By filling actually these remaining tetrahedral voids, one really can create, even in the very simple case of an ASA potential, potential that almost matches very nicely on full potential or the exact potential. So to summarize, we need
I think your microphone may need a little adjust.
Yeah, so maybe you have to speak up a little. Maybe that helps.
Oh, okay. All right, thank you.
Yeah, I have these issues quite often actually. So maybe if I speak up, this helps. So to summarize, basically we need this empty site. So first of all, to reduce, if you just do very simple ASA calculations to reduce the overlap. We also need them to approximate the potential in the interstitial regions better by some local spherical potentials. And actually we also need them in full potential calculations. And in this case, it's actually for ensuring the convexity and also the sphericity of the polyhedrons that tessellate the space. And effectively, by introducing such spheres, we can really practically lower than this L cutoff and also achieve convergence. However, placing such empty sites is actually not really a trivial task, and there are quite a few requirements that we need to satisfy. So firstly, this additional site should improve really the description of the potential. And this can be achieved by putting them or placing them on really some high symmetry positions. And ideally, one should also minimize the number of additional sites that one places in a structure. And so if one really wants to also then make an automatic algorithm that does all of these things, one should try that one places the sites in a way that one doesn't change the space group symmetry. And because this can cause potential artifacts in the electronic structure. So already quite some time ago, an algorithm was proposed by Jepsen, and it was also implemented in the Stuttgart code, here in this LMTO Stuttgart code. And basically what I'm doing is following this. So in this, so here's the outline of the algorithm. So atoms are here represent the spheres. So in the first step, one subdivides the lattice of the structure by some general grid. And then for each grid point, one first of all generates a whole set of empty spheres by applying all the space group operations. Then secondly, one calculates the sphere radius of all of these empty spheres by basically by maximizing the overlap with the atomic spheres. And it's basically one has to eliminate the spheres if one is, for example, inside another atomic sphere. But now actually 3 cases can happen with the overlap within the empty spheres. So first of all, the overlap can be acceptable. So the empty spheres can be just touching or slightly overlapping. Or the overlap can be also huge, for example. And if the overlap is huge, this is a good indicator that the sphere, actually the point, is quite near a high symmetry line or high symmetry point. And by merging this whole set around this symmetry line or symmetry point, one gets closer to the symmetry point. And yeah, the third case is basically if none of those apply, then one just omits this for further discussion, for further consideration. However, there are some issues with this thing. So first of all, if the structures gets really complicated and more complex, then one needs really a very dense mesh to sample basically the structure and to get a nice feeling. However, this also means that there are then a lot of points, and this means that it's slow. So one way how to reduce this is that one just does the search in the irreducible wedge under the space group symmetry. However, finding this irreducible wedge is actually, if one does it just straightforwardly, it is a really heavy task because if the mesh is really dense. It's a really bad scaling algorithm with a lot of finite precision floating point comparison, where one also has to take into account some tolerances. However, so we basically now, to circumvent this whole problem, we generalized an hash-based approach by Hart here to also space group operations. So he just used it for basically point group operations to get these irreducible wedges for the K points. And this basically leads to an almost linear scaling algorithm. So normally what is done there is, so if one applies, so for every point, so for every vector in lattice on the grid, one applies the space group operation and gets a new vector. And then one has to check by looping through all vectors and see if this vector has already been considered. And this is this heavy operation, yeah. However, by changing now the representation from the vector from these 3 floating point numbers to an integer number, which can be done by some transformation, one can already save some time. And it's also then possible to transform these 3 integer numbers that described in this vector into a unique hash, which is really specific for every grid point in this subdivided lattice. And then one doesn't need to loop anymore, and one just needs to check if one has considered this certain hash already, and then it's really a blazing fast algorithm. So in the end, one one arrives with a very efficient and fast program. Here you can see a code snippet. So the program has a Python API, which is easy to use and has already adapters for some common, I would say material science libraries like ASE and PyMathGAN. It is, the computational heavy part is written in Fortran, and it's also parallelized with OpenMP. And yeah, last but not least, it's also fully covered by unit tests and also regression tests. It follows our modern software development principles. So now I want to show you some structures and some results where this has already been used. So I think the first one was about placing empty spheres in some grain boundary to calculate actually the solubility and segregation tendency of bore in grain boundaries in paramagnetic iron. And here, for example, the tool suggests that 4 empty sites here, 4 empty spheres in these sites on the interfaces, on these interfaces. So this whole thing keeps the inversion symmetry, and it really makes the structure ready for, in this case, calculations with EMTO. So then the next thing is actually my calculations. So it's about modeling dislocations with KKR methods. So dislocations are basically line defects in crystals. And so they're effectively modeled by some so-called elastically balanced dipole approach. So so this is generated by orienting this DCC surface into this 111 direction, and then according to this cut, the atoms just displace perpendicular to this plane here. You can see something like that, and this creates actually dislocations. And it's not really a problem here that one gets huge voids. Yeah, so the structure is still filling, but actually there is a problem with the polyhedrons here. So they get quite skewed, and of course one can just take high cutoffs here, but this is usually not really possible. If one wants to do, for example, LSMS calculations with some nonlinear spins, then yeah, so then one has to stick with some lower L cutoff. And effectively, this algorithm puts in these spheres or these additional sites along this dislocation line, and when it just adds 2 additional sites to this 135 atoms here in this structure. So it's also not really a problem of performance. So, and then something else. So since we have implemented some component resolved block spectral functions, just wanted to show you how the placement of empty spheres can help improve in the band structure. So you have this titanium deselenide 1T phase basically, with the titanium atoms here and the selenide atoms in these 2 places here. So if one does ASA calculations without spheres, of course the band structure actually doesn't really look that bad. I mean, but still all these degeneracies and things like this, and also the density of states often that correct, also not the placing of the Fermi level. And then by really placing the spheres gradually and also optimizing the radii and things like this, one can achieve even with simple ASA calculations a result that matches some more precise calculations. So you really see, for example, how this degeneracy here changes. And yeah, so this is kind of an extreme example. This is a layer structure of molybdenum deselenide with some lead here. And calculating these structures with KKR methods. So with KKR, it requires a lot of empty spheres. But this was, for example, the best thing that our algorithm suggested, and it actually works also to calculate it in that way. Because I think even for full potential methods, this is already too big, such a structure. So if one wants to get rid of the empty spheres. So yeah, I want to thank my supervisor, colleagues, and funding agencies for the support, and thank you for your attention, and I'm happy to answer any questions.
Okay, thank you, Franco. It's very nice. But somewhere your sound is a little bit very fuzzy. But
yeah,
also the idea that, of course, empty cell is very important when you have large space, especially for multiple scattering methods that we need filling certain a number of spheres. My question is, how do you determine the size of the empty cell spheres? Are they all the same, or are they, or you just wait to the radius empty sphere? Do you adjust them, or what's the principle for determining the size?
You mean how I determine the size of the sphere radii?
Yes.
So initially they're determined by by basically a certain overlap or no overlap. For example, that I just place them in a way that that it's just touching, for example, and yeah, then one can increase them. But it's of course an iterative procedure. So one puts one empty sphere, and then this whole algorithm starts again, and then one places another empty sphere, for example, in this very open structure. And then, for example, the sphere radii will be, of course, different in the case of this titanium diselenide structure. So there will be two very large spheres, and then the other four will be quite small. And yeah, so for example, the initial sphere radii of the atomic spheres is just, well, I just found by doing some Matisse constructions. So Matisse constructions, you basically overlap all the potentials, and then you just find the minimum between them. And this mostly gives you a quite accurate guess for the sphere radii ratios, for example. And for the weights, if one does tessellation. Yeah.
Franco, thank you very much. Very nice talk and interesting. I'm gonna to use it. What kind of materials are you gonna to study next with this?
Well, me personally, I'm just studying effectively BCC and FCC materials. But there are other people that we're somehow collaborating with that they also study more functional materials.
Mm-hmm.
And for them, it's more important. So, because I mean, in BCC and FCC, okay, if you introduce defects, then
and this can be applied to high entropy alloys as well.
Yeah, I mean, if you, of course, if you have some defects, maybe it will improve something to place their empty spheres. But if you just have a normal BCC or FCC structure, I don't know if it really would help something.
Thank you.
Yeah. So, sorry, I missed the beginning of your talk, but so in the end, that you treat these new sites and do a lot of careful manipulating to make sure that they presumably satisfy as many of the overlap conditions as you can do, but still within each sphere in the ASA, presumably you're still doing a spherical calculation in that sphere, right? There's nothing non-spherical about it. Is that correct? Do I understand correctly?
Yes. So I mean that's somehow Yes, exactly. Of course.
It's fundamental to the ASA itself, right?
Yeah.
Yeah. So the question then arises: Have you looked at any systems where you can do the very best you can here, right? Which is very nice, but then go to FLAPW or something and see what the remaining errors are that come just from the sphericity inside of all of these many spheres. Do you have any feeling for that, or has anyone looked at it? And I presume it's system dependent, and if you're in presumably if you're in an oxide or something like that, these things become more troublesome.
Yes, so maybe, so let's say like this. So right now it's just like an algorithm that produces empty spheres, but I'm really trying to find a metric, for example, that tells me if what I'm doing is correct. For example, one thing is that one can just calculate electrostatics with ASA and places the spheres there, and just interpolate some density that one gets from somewhere else, like from some full potential calculations, and then see how good is like my electrostatic description, for example. So this was one idea on how to see what I'm doing is somehow correct, and really saying that this is more or less an exact metric that tells me if even this placing of empty spheres makes sense in the ASA. But this is more or less an idea. This is still an idea, so I have not done that yet. Yeah.
But if you say this group that you're talking to with the full potential KKR methodologies, and I presume that the full potential part of it, does that, the question is how much of the sort of fewer spheres and what have you, but doing full potential on those spheres would be adequate. And I guess you don't have any feeling for that, but but if you do, I'd be interested to hear.
Yeah, so I cannot really, I cannot really tell you now. So I don't really have a gut feeling about how to place correctly and how to, or what are the errors. So I cannot really answer that at the moment.
Yeah, it looks really nice. Yeah, thank you for the talk.
Yeah, Franco, I think maybe we can try silicon. I just had a silicon down with full potential KKR. I found something very interesting. Maybe next time I'll keep a talk about our approach to full potential calculation of silicon. Have you tried silicon? Is energy versus lattice constant?
Actually, I haven't tried that, so I haven't really looked at
silicon.
that.
I found it's interesting. It's not many. I haven't seen many results in literature about total energy calculation of silicon. People mostly just pick up equilibrium lattice constant from experiment or whatever, and just calculate band structure, try to find it. I really like to see how the total energy versus the lattice constant. Just give this parabolic curve. I found it very rare. This such a result. It would be nice to. I found a few, but it would be nice to you do the calculation. It's easy, right? It's just silicon to see. I know you found the empty sphere there. You must have an empty sphere. So
yeah. So this is also tests. So this is also
just run a silicon, and I'll show my result. We compare like say total energy or.
Yeah, I can try it.
Yeah, let's give it a try. Maybe next time I'll talk about what I found is something empty sphere size also is kind of relevant.
And yeah, so maybe one thing that I actually wanted to try with your code, but I haven't had time to dig that up. So just calculate. So basically interpolate the density and then just calculate the electrostatics with the full potential code. and then see how well I can match it with ASA or just some muffin tin.
Yeah. I also happen to talk to a person who is working with Dwayne Johnson on developing their own full potential KKR code. And they told me when they set up this radical plan between atoms, but if the same atom, maybe radical plan is right in between. But if two different type of atoms, or maybe that's an empty cell, right?
Yeah.
The way to set up this radical plan in between atoms, the way they do that is they calculate the charge density between atoms. They find where the valley is or maxima is. So they put the radical plan right there. So each iteration, they changes the location of radical plan, and they found it's very important. Yeah, I think we need this also in our code. I think that's probably very useful.
So I have something like this too. But for example, I found that overlapping the potentials gives better results, or like gives better guesses than, for example, overlapping the densities.
Okay. Yeah.
I mean, one can do so. One does basically some so for a priori, so one does some atomic DFT calculations, get the density, get the potential, overlap everything, and then check it. So that's how I, for example, find the sphere radius or the ratios between the sphere radius initially.
Does your code for generating empty cell is freely available?
Not yet. Let's say.
Yet.
So there are some, yeah.
Okay.
But one can.
We have this position generation utility code in a must. For generate large, but usually for like a structural material without much defects, maybe you're fine. But maybe eventually, if we have a large voice, that can be part of our position generation. So it automatically produces adding empty spheres. It will be very useful, because so far for smaller system we see by eyes.
Right. Yeah.
Brain. Though hopefully they will become automated. It will become very useful.
I mean, even with the grain boundary, like it's really hard to find it already by eye. So
yeah.
It's
and especially if you get larger and larger cells, as we want to do in LSMS.
Yeah. If you have 1,000 atoms, then where do you put
Yeah.
You can't really place your empty cells by hand anymore.
Yeah.
And this is also the reason why, for example, I re-implemented it. I mean, there is this EMTO code, which works really fine for small structures. But if you try to do that even with a grain boundary, like you're going to wait a long time. So this was actually the main reason for doing this whole thing and implementing it so that one has control and optimizes that.
Great, thank you. Let me stop recording so we can start to chat something else.